goal is to graduate my MBA.
You're being recorded now, by the way. And you're on just 5 people. So you can go ahead.
If I can survive advanced reactions, no, just advanced reactions. That professor just sucks.
More power to you. I could not get my master's in 2 years.
Were you in the rotation? No, that was my year.
My goal is down, so they're like,
And why don't we get started? We're dwindling numbers. With all the good people here. So hopefully, I don't know. Anyway, I didn't put this up here, so. Yeah, eventually we'll just go straight on Zoom, it's like, seems like that's kind of the direction we're going. I guess I could give, I don't know, I've given out grade boosts already, so it's kind of like there's nothing left to give to channelize people to come in. Oh, did you talk to anyone about the,
We couldn't get a hold of them back there. I
Right.
thought I'd talk to them today, but they didn't show up today, so.
oh, yeah, right,
or I would like to go, but I probably won't be able to go because I'm literally on campus from 8 a.m. to like 4 p.m. every single day.
Oh.
But if for some reason we do it over the weekend, I would love to join, but I know that that's probably not anyone's coming.
well, the places are closed.
Yeah.
You can't go in, I think.
So,
Which place was on that?
Well, first Lyondell. We could go to a bunch, we can go to the recycle center. And then the Cross Mafia in Kentucky. And then Millicron. There's 2 extruder companies.
Okay.
That's 4. I mean, I could dream up some more. Look like people want, like pigment companies, the additive companies, film blowing companies. I mean, so there's 2 pigment companies in Cincinnati. There's kind of like companies, I don't know if you heard of people co-oping.
connected to PNG, more if you want me to like send you a contact, you want to go there.
Like all right, so there's a research part, there's like the processing part's the interesting part, and I don't think they'll do a tour. Do you know anyone at processing that does polymer processing, like bottles and things? And because they have a whole division for that.
I
And
know about processes when they make hair care
Yeah.
products and deodorant. I don't know about plastics, but I could,
I mean, hair care might be okay, I guess.
and I know the people who give tours of like that, like,
Mhm.
of like the thing, because like I've worked there and I've seen people do tours.
Yeah,
Like that.
yeah, that wouldn't be hard to do. The central research isn't hard to do, but they don't, I don't know, it is spread out now, and it's kind of, so it isn't all in one place, and it didn't seem like they had that much there. Lyondell has like both manufacturing and research stuff, so it's kind of good to go to. Anyway, we could do P&G too if you want.
Well, I mean, I probably won't be able to go because my class, but if people wanted to.
Yeah. Well, so far, no one wants to go. I mean, except this one person that's firmly committed. So anyway, if you could come up with a time that's good for you, and then we can just see whoever else will show up for that.
You know,
You know what I mean? So just email it to me. And then,
also like a list potentially.
so like Fridays, I think that at Lyondell, they don't run the machines, the big machines on Friday, which means it's safer. You know, but basically, I guess it's more interesting to see the things with stuff flying around. So basically Friday isn't a great day, but I've done it on Friday before and it was fine, so. And if we do the recycle center, they like to go in the morning, like 8 o'clock or earlier. So you might be able to make that if it was like 6 in the morning. It's like, oh, if you'd probably be the only one showing up, right? So anyway. I think a tour would be pretty good, but I think you get a lot out of it, but basically no one wants to go, we can't really do it.
I think probably in other classes, if it's not the days that I do research, I might be able to go if I like tell them why, but on Tuesdays and Thursdays, I'll get a 0.
Oh, maybe you should do that. Give out zeros. when I did that in the other class, all of a sudden, like, well, I got 3/4 of the people to show up. When I said you kind of had to be in there, I was taking attendance. So that does kind of work. But anyway, to me, it's a little, I don't know, it seems kind of dumb, but anyway, so we got this paper. So it's actually in the same issue as that one of the other papers we looked at. So it's like this year. Anyway, it's a group from China. I don't really know schools in China. It's pretty good work, I think. National Key Research. And oh, that's who funded it. And they're at the State Key Laboratory, which sounds important, but I really know nothing about China. So anyway, so there's this idea about all right, so their reference one is this paper, which I haven't put up yet, but and they talk about the free energy landscape. And this is kind of the classic picture of it. So so basically, like you have a protein, and it's going to fold into this small compact structure. Which paper shows some of the structure, like alpha helices, whatever it's going to fold into, some compact structure, and it's got some one active site where the protein's going to act. Right. So people have thought about first understanding this process. So there was a lot of money in the 90s, I guess, to understand this process, and that money all dried up. So then there were a bunch of people like this guy, Dill, came here to give a seminar about like 5 years ago, maybe. And I think I asked him, like, what are you doing in protein? Because he's an expert. He founded the field more or less, He's like, oh, we don't do any of that anymore. There's no money in it at all. And he's doing some kind of drug delivery thing. So basically the bottom fell out of this in terms of funding. It's interesting, but basically there's no money in it anymore. So people don't do it. So Dill, I think, came up with this idea of free energy landscape with this kind of funnel thing. So actually, there's many dimensions to this, more than 3, to the folding process. So mapping it out in 3D or in 2D projection of 3D isn't really that meaningful. But the idea is you have these high energy states, and then like say a group here wants to bond with a group there due to hydrophobicity or polarity or disulfide linkages, things like that. So it wants to reach this final state, which is a compact structure, but it's in this loose state. And then there's something called the Leavenworth's paradox, which is that the amount of time for it to randomly find, for one protein to randomly find its native state by random trial and error would be like longer than the time of the universe. So basically there's a paradox that it can't happen. Like it can't actually have life because it can never actually reach that state. So anyway, in reality, what they found out up until like 2010, when no one was doing this anymore, so there's folded proteins, there's unfolded proteins that act kind of as chaperones. They call them chaperone proteins. The hands of these things and force them to fold in the right way. It's like a pair of hands kind of folding a paper airplane or a bounty or something. So basically there's other assistant proteins that their task is to make this shape show up. I mean, naturally has the bond links to make that in the functional group in the right spot, but in order to reach that state, it's not that easy to get there. So move up to today, like 2024, they're still talking about the funnel. So he says somewhere in here, the funnel, like if you look, so have a funnel shape. So he's talking about that paper. Reference 1 is that paper, this reference, that Dill paper. And then he's saying like, well, there's like 50 up to 38 papers, or 37 because he used one for Dill, 40. So 39 papers recently within the past couple of years of people trying to do this with synthetic polymers. Right, so the idea, so this is called a single chain nanoparticle. So you have a polymer chain and you collapse it down somehow into a cluster. And then his idea is he wants to have like functional groups on the surface so they can further grow things. Like he's gonna grow some of the structure. And the last slide he shows that he's grown these things. Like this is where he's formed these things with the thing sticking out the surface. Oh, he makes it so that the things stick out on the surface, and then he cross-links along the surface, so he makes like a shell cluster thing with the polymer stuck in the middle, right? And then it's a nanoparticle, single molecule, and then it can search out, it's got these bonding groups on the surface, it can hook up with other, I shouldn't use the word hookup, but basically hook up with other little spheres and then make structures. And if you could tune the kind of the shape of those linking groups on the surface, then you can control the shape maybe of these things.
So that figure showing that it's going from a single particle size in A to the longer chains in D.
Yeah, that's the idea. And the idea of this, so people go further than that, like if you have a flock of geese, right? Then like for each goose, I mean, and this is throughout other areas too, but basically, or starlings or something. But for each starling, there's a very simple set of rules. It's like have a guy on your left that's further up and a guy on your right that's further back. Just two rules. And then you can make this V thing. And then with starlings, this equivalently simple set of rules that make it into this cloud that takes all kinds of shapes, right? So the idea is like, well, just give it like one or two rules and you can make, the Eiffel Tower out of these things if you want, or anything you want, some machine, a gear, a little rocket that flies around or whatever, see on a nanoscale, it's 200 nanometer, right? So that's somewhat of the goal, I guess. Anyway, no one's done anything close to that. And he's got a hypothesis here. So his hypothesis is that everyone else just took a polymer, stuck the functional groups on the side, and then in a good solvent, so our expanded coil reacted it, and they get something that isn't collapsed, So what he's done is he's taken like polystyrene. So if you polymerize the double bond, you get polystyrene. Then this is an acrylate, so that acrylic group is here. That's a hydroxyl, and that's going to make a super absorbent gel, right? And then he sticks this function, I think it's benzylphenone. So it's got this group can UV radiation will come in because it's like an antenna because it's conjugated. So it's like double single, double single, double single, double single. So that's like an antenna for EV radiation, particularly UV, because of the length of its long. So it goes into the higher energy realm of visible light. So that thing can suck up a lot of UV light, and then it can form a free radical, and it can polymerize with, so two free radicals, I guess, combine, and it makes a bond. So it links up, make bonds the surface of this. So he has some that are bridging across, and then some of them are left unreacted. They don't completely react. So then those can be used to react to the next stage. So it's a hierarchy. He makes this. So what he does is he makes that polymer, and he shows it as a block copolymer, but it's actually a random copolymer. Oh, yeah, he says here, random copolymer. So there's some problem with random copolymers, that the reactivity of the two groups aren't equal, right? And also they may be more reactive. All right, so this might be, so you have this bulky side group. So that's not going to want to bond next to another bulky side group. So more likely it would want to bond next to this. So you get something like an alternating copolymer, like you'd have styrene, acrylate thing, then that. Then this other group that he has on it, this sulfate, because he's using raft, he has to have that protection group for the free radical. That's like the leftover of that, I think. He doesn't actually say that, but I think that's what that is. Like that's your protective thiol for the free radical thing. And it ends up being at the end of the chain. So anyway, so the raft, like any idiot, can do this polymerization. That's kind of its theme. And then they're just doing, and you can do it in your bathtub because it is not sensitive to water or oxygen or anything. So he goes ahead and does it in China, makes this thing, and he ends up with this stuff. Then he says, like, he has a solvent, I think toluene, that's good for both. That's a good solvent. And then he has acetone, that's a bad solvent for polystyrene. And it's a good solvent for this thing. So basically, he puts it into acetone, and he also does it in THF, and then he gets the thing to collapse down. And then these things are sticking out, and then he irradiates that with UV. This kind of compact fluorescent bulb is supposed to be the UV source. So he's UVing in this purple. I guess purple means UV. All the codes are there. When I first saw this, I had no idea what he was doing. I thought it was like Like instead of having an incandescent bulb idea thing, like the woman's having an idea. What it is, it's supposed to be purple's UV. This is a UV source. So he has a special kind. You just take your beaker and put it under like a sun lamp with aluminum foil around it because the UV causes skin cancer, and then cook it for a while and then get your stuff out. So he does that, but mostly he does this new trick where he runs this tube around the UV lamp and he flows through it for a certain length of time. And apparently the combination of the flow and the fact that it's wrapped around the tube gives him like super cross-linking. Like it works better that way. So one of the points is that he has a better way to do the cross-linking. There's a few things in this. It's not a bad paper, I mean, there's a couple things missing, but I think he was limited in equipment, I guess. But anyway, so he does that. So he has the two cases like that one, polymerized in good solvent, this thing polymerized in poor for the polystyrene, and then he can link this up and make these particles. Then he's sticking that into a, all right, so first he does,
Wait, quick question about this figure. Does this B lead into C in that figure? So, or does it
No.
start with two different things?
it's the same thing. This is in toluene, I think, good
Okay.
solvent. She says good solvent. All the keys are here. It's just that it's not logically put together somehow. It's not like an Apple thing. It's like a clone thing, whatever. Right. So it's like somehow you can't figure out. Yeah.
So he's starting with the extended self-voiding polymer
Right.
chain, throwing it into toluene, and it forms the loose and sparse.
No. He takes that in toluene and then he zaps it with his UV. That's the purple.
Got it.
That's right. Good solvent, purple. The lamp's here. The guy's happy. He makes this thing which has some clumps, and then it's got the chain. So this is all right. So in protein language, so if you go back to the dill thing, you'll find out that he says the protein goes through this extended coil thing and then forms a thing called a molten globule, which is it's a 3D object, but it's not the native state. And then it rearranges into the native state, which is functional. Right. So that's kind of the scheme of things. And then a monkey wrench thrown into that is that these chaperone molecules that help it fold aren't folded. They're just open chains and they just have functional groups that kind of guide the unfolded thing to where it's going to go. So anyway, there's three classes. There's four classes. Is extended chain, molten globule, native state, and then functional or natively unfolded proteins. All right, so you have these kind of motifs that he's going to lift over here and say, well, this is like a natively unfolded protein. He mentions that in the paper, or you could say this is a molten globule, like it hasn't reached what he wants it to be. It's these kind of globular structures connected together by chains, So it kind of fits, the whole thing fits in with the biological mimicry thing, in a lot of ways, but
I just have a question, it might be like explained in the paper once you read it, but like, what is the benefit to having like a protein that's like more like extended versus like more like collapsed or entangled? Like, does it like make it not work as well, or?
yeah, it makes it not work. Say this is actually going to be an enzyme, right? So it's a catalyst. Then you want to have sites of perfect geometry. They're going to hook up to like glucose or something and break it apart, right? Or it's going to hook to two things and make them join together. Like a catalyst joins, like polymerization catalyst would join a chain to another monomer. It has to be an exact shape, and it has to have exactly the functionality where you want it. And given that the thing is going to have billions of conformations wiggling around with KT, it's not going to work. It's got to have one conformation that has 0 entropy. The other thing has gazillion entropy, right? So basically you can't have life in that state, at least not that you couldn't have life that way. You'd have to have organization. The only way to get organization is to have 0 entropy. So these are 0 entropy. This thing has a lot of entropy. And the molten state also has a lot of entropy, if you want to look at it from that perspective, right? So you need that to make it functional. So these are all ideas. The fact is that I think something like 80% of proteins are unfolded functional. So we know nothing about those. Because the folded ones, if you get that one that's perfectly folded, you can crystallize it. Even a small crystal, it's hard to do. And then you can do X-ray diffraction on it and like rotate it in 3D space and get the exact structure of that thing. You can map out, and that's what the protein data bank is. You can also use NMR to find where the functional groups are, how they're related to each other. So anyway, there's advantages to having perfectly full, and the reason that we've studied mostly that is because you can characterize it, and the other ones you can't characterize. Although that's going to change very soon because the brightness, so this is all done with a synchrotron, like an X-ray source that's like a mile diameter ring that sends around subatomic particles, and where it turns corners, X-rays are given off. Right, so, and it'll have like 50 different instruments on it, or maybe 100, so anyway, so protein crystallography was the thing that drove that, because if you find the one magic shape that cures cancer, then like this unlimited money will pour into your pocket. That's basically they're screening every possible crystal that they could form, like 24 hours a day. It's just like robotic testing done on that. Now you get a 3D graphic out of it that's its structure. I mean, they have like rooms where you look at the molecules in 3D and you can twirl them around and see how the two things would fit together and stuff. So there's a lot of money. This is like the dump truck of cash has flowed into that. Anyway, so and it's basically funded all the synchrotron building, which are like $200 million instruments, I guess, something like that each, And this in the US is there's three big ones, I guess. Europe has one big one, two big ones, and so in Japan has one, China has one. So basically all the big countries have these.
So the Oak Ridge National Lab.
Oak Ridge has neutron. So that's different. So that's actually, and like, say they have a 60 megawatt nuclear reactor. So a power reactor is like 100. That's almost a power reactor. Like you could power a city with that reactor. And then they also have a spallation source. There's a long story to it, but Al Gore is involved. So he was anti-nuclear. Then they were talking about building a neutron source at Oak Ridge. He's like, yeah, in Oak Ridge in Tennessee, where he's from. And then it got to be, they had all the plans, they were digging the dirt. Then he said, then someone told him it was a nuclear reactor. So they axed it immediately when they decided to build what's called a spallation source, which is a big linear accelerator, which also feeds a synchrotron. And then you make, I think you send protons down it and they blast into metal. And when they blast into metal, they give off neutrons. So there's no nuclear reactor, but there's like a lot of radiation going on, and mixed radiation. And in the accelerator is pulse. You have to pulse all your experiments to that. So it becomes more complicated. That was $1 billion thing, the SNS. And the HIFER has been around a long time, but basically that's also probably 500 million. Put that thing together, but anyway, so that's also big money science stuff. You apply for time on it and you use it. But anyway, so that said, so basically he wants to get this scenario. So he just shows that he does that basically. So he gets the so he does this, he does dynamic light scattering. Okay, so it's going to give oh here. Oh, I'm on paper. So we'll talk more about dynamic light scattering, but basically for the purpose of this thing, so you're going to have your stuff wiggling around with KT, and then you're going to shoot a beam of light on it, and then you're going to pick up the intensity at some point, and that intensity as a function of time is going to be squiggling like that. You do a correlation between time for different delta t's, like is that point correlated with that? So if it's the same point, it's 1, and if you get further apart, it decays down. And from the way that decays, you can get the mean squared position of the atom, and the mean squared, if it's diffusion, is 2dt. Right, so you can get the diffusion coefficient. And once you get the diffusion coefficient, you use Stokes' law. So you have KT over 6 pi viscosity. So in that case, would be like an other usually, and then a hydrodynamic radius. And 2 times the hydrodynamic radius gives this hydrodynamic diameter, which he likes because if you draw a picture of a thing, I mean, a diameter is kind of a more nice thing to do. And plus, if it's a sphere, then that technique should really work, So he shows that when he does it in a good solvent and toluene, he gets a larger size and it gets smaller when he puts it into acetone. Oh, sorry, yeah. This is a hydrodynamic diameter calculated from that machine. from that dynamic light scattering machine, which is one down in the characterization center, and then in the good solvent, it's 5.62 nanometer. Once it collapses, it's 4.26. So it's kind of a 1.5 nanometer change in the size over 5. So whatever that is, 20-30%. Then, I mean, whenever you synthesize something, you kind of have to show that you got what you say you got. So NMR is a way to do that. So that's this. And you don't, I mean, basically there's a fingerprinting that goes on here. See, he's labeled all the groups and he's labeled kind of the peaks that associate with those groups. That's kind of an easy way to do it. And then he does something called NOE spectra, nuclear Overhauser effect. That's like a one spin. So it's the nuclei are precessing, and when one's near another one, the spins of the two interact with each other. And so there's a time dependence to that. So if you do a pulse and then watch the decay of the interaction, you can measure the distance between things. So I mean, it's important here because in this case, he's saying those things are far apart, and in this case, he's saying those things are close together, right? And then also, he talks about the contour length. So this is a good paper for us because he's talking about the contour length, which is not the length from here to here, but the length if you took the curvy road, right? So that's the contour length of the chain. So there's a contour length between these functional groups. And there's a contour length between the functional groups and the folded thing. So in the folded thing, the contour length should be far apart. And in this one, the contour length should be close together between that red group and that red group, right? So he says he's getting that because this peak in the NMR shoots up when he does this time-dependent NMR test. It's that big peak here tells him that they're close together. I guess they're close together in the non-solvent. So this one's toluene and this one is acetone. So acetone's the poor solvent. It's got a bigger thing here than the toluene. That means that confirms more or less that he's got this geometry to the thing. I mean, he shows a bunch of things that are not proof, but they're kind of like go along with that cartoon. You know, so he's kind of there in this. The one thing that's really all right. So then he does this. He shows the molecular weight. So he sticks it in a GPC column, right? And I mentioned before, like how roughly how a GPC works. You have so you're going to have a gel, like a styrene gel and some solvents. You pick different solvents and you're going to inject a small amount of like 10 meg per ml, so like 1%. So dilute, right, of your polymer. And then it's going to, the things, so this is really high pressure. So it's high pressure liquid chromatography, also called size exclusion chromatography. So basically, but it's very slow flow rate. Like the flow rate is like 0, right? So the things that get injected here are randomly wandering around by KT. So they're diffusing, right? So the big things, so if you think of that thing as a bunch of core structure like that, so whatever. So the big things, the small things can go explore every possible crevice of this. It takes them a long time to get through because they're just spending most of their time doing the tourist thing. Whereas the big things are just like businessmen and they're just going straight through the thing. So the early time is large and the small time, the late time is small. The early time's big, the small time's small, the long time's small, right? So it's an opposite thing. You think the other way, but basically that's how it works. So with that, and all right, so and at the other end of this thing, he's got an index refraction detector, right? Some kind of reflection, and you got to get the index of that from that, right? So it's the simplest possible detector. So, and cheapest too. So that's like the $1 sign detector. So that just gives you like the amount in there versus time. And then again, the big things would come out first, the small things would come out later, right? So you want to get molecular weight out of this. So you stick in polystyrene standards of known molecular weight. And they come out like the standards are going to be like here, and then you say, well, my stuff is, you can make a plot of like molecular weight versus time, and then you can just say, what would go the other way. And then you just say like, here's my standards and here's my sample. So that's the molecular weight of my sample. So it's a polystyrene standard molecular weight. I mentioned this because his molecular weight changes, you know, when he goes through this routine, because he's not really measuring molecular weight, he's measuring the hydrodynamic diameter of the particles as they diffuse through this porous structure. Right. So molecular weight, he gives a number of molecular weight, it drops, but it means just the structure got smaller. Right. So he shows that as corroborative evidence to this dynamic light scattering. And he gets the same, oh, sorry. He gets the same result from that. So here's these elution time, and then the big things are going to come out earlier and the small things come out later. And these are the time, whatever. And then he gets that molecular weight. So it's not really a molecular weight. It's actually kind of a hydrodynamic radius. Right. And then he shows when he does it in batch, this is his tube exposure time within his tube flow irradiation thing, or he can take a beaker and just blast it with UV. So the blast it with UV is a star, and these things there. Crosslink and toluene, you get this thing goes that way. So he's showing that the thing gets smaller and it reaches a plateau. It means that that's where he says it's in native state, like it's fully collapsed. And no matter how, so he varies the number of side groups on it. So if you vary the number of side groups, degree of cross-linking, the number of cross-linkable groups, the acrylates, he also gets a plateau. And he's running, these things are run at 4.7 or something right here. So he says he's reached the native state. It doesn't change after that if you run it longer. Someplace he shows this running for a day and he gets the same number. Right. So he says he's reached his terminal collapse state for the thing. So that's good. I mean, it's nice. So what's the problem with this? Well, I mean, this is a goofy way to do it because like you can buy it and you can buy a GPC. So it's going to be like 10 grand more to get a light scattering detector. And then 10 grand more, you can get a rheology detector. So there's two other kinds of detectors. So just a matter of 20 grand over his 50 grand he paid for the GPC to put the other detectors on it. Then you could actually measure the real molecular weight, not the styrene standard molecular weight. Then he could show nothing happened to his polymer. It's the same molecular weight. Like it went through this process, it's the same molecular weight. It's the hydrodynamic radius that changed because the rheology radius would change. And also this diffusive radius would change. Right. So if you do the double detector, triple detector, you can tell everything about the thing instead of using the one index detector. And it's kind of goofy they didn't do that. I guess I'm not sure why they didn't have a better GPC. You know, that would have been a nice addition. That's the only real flaw in this paper, is that he should have used the multi-detector GPC. If he didn't have it, he should have just taken it somewhere where they did. Anyway, but that's okay. And then also because he didn't have the detector, then he had to do computer simulation. So he uses he uses this Homid blue oh, it's me that's making that noise. I was looking within this thing. It definitely says Homid blue in here somewhere. Let's see, maybe I'm not actually in there. No, probably just blue. It may have, yeah, no, blue is actually the color. There's only one blue. So how about I look here for blue? Blue, here, Homid blue, there. So MD's molecular dynamics. This is a package like, it's a competitive package to lamps. Like you can Google that. So they also have a web page. It's from the University of Michigan. The Glotzer, Sharon Glotzer is the person that does that. So anyway, they have a web page. The problem is, like the lamps, there's so much stuff online, and this is less people are using it. I'm not sure why he chose this to use. Like it's just a preference, right? So he used that, and then he got from that he got a couple things. He got a picture here somewhere of what the structure is in this paper. These are from Homid Blue. They look like he just drew these, but these are actually the simulation results. And then he shows, so from that, he can calculate the razor gyration of the, this is also, so after he says they don't agglomerate, he shows it in Homemade Blue that they don't agglomerate by doing it. So this is the gray thing are water or solvent atoms, and the blue things are his things. Right, so usually you do an implicit solvent, so it'll just be like, you don't see the solvent, just say it's an interaction. And then he's actually put in solvent things, so it's kind of nice. And that's in the supplemental, so anyway, he gets these pictures from it, and then he can calculate, because in the simulation, you can take any part of this molecule and just say, where is it? So he says, like, where are these benzylphenone groups in this thing when it goes through this good solvent, bad solvent, which you get by just changing the interaction energy in it. So it's just like a knob you turn, right? So, and then a lot of computer time. So he says, like, when he's in a good solvent, the X is the contour length distance. So along the squiggly line, so following the curvy road, how far do you have to drive to find the next benzylphenone unit, right? So when you're in the unfolded state, you drive not far. So the ones that are close to each other are close together in the contour length also. And in the one that's folded, he gets what he wants, that these are a long contour length distance apart. So we talked about contour length. This is a measure. X is a measure. He does it in a computer simulation. He finds out that they're separated at a fixed distance, and that distance kind of correlates with everything else. So that works out pretty well. And then not sure what this one was yet. I don't remember what the distribution of distance of the reactive units to the center of mass. Oh, he's shown that they are all on the shell surface. It's like if they were uniform within the sphere, right, then this would just be a flat number. And then we cut off at the edge of the sphere. But instead, like, he's got a peak at 1.5 nanometers, and his particles are, I forget what, 2.5. So that's, and the peak, I think that's a radial distance. It's basically definite, like, at the surface, right? So that shows that his thing worked. I mean, in the computer simulation. So, like, he's got quite a bit covered here. I mean, he's basically covered all the bases with it. Anyway, I forget what this is. All right, so one other problem is TEM. Like, so the TEM, he takes that solution of the stuff, he dries it out, he does a couple other things to it, and then sticks it into a TEM, where probably the residence time in the TEM is like 1 second before it burns. He doesn't mention that. So basically, whether these things mean anything is, he has AFM and TEM. AFM might be better, you know, but basically both the TEM here and also the structures, you have to kind of wonder what's going on. Oh yeah. And then, oh yeah, so he has scatterings. This is like actually a main point of this. Last question, but so he's got this 1.7 dimension thing, right? Which is so that's what's predicted by the computer simulations for good solvent chain. So he's got that. He measured the X-ray scattering, and then he got that 1.7. And then he shows that when it gets dense, you get this kind of parode-like minus steep slope, which means a surface. So if you let's see. So the steep part we didn't talk about, but basically, oh, he also does the RH by RG, because he gets RG from the computer simulation, RH from the dynamic light scattering. So anyway, if you say that the scattering intensity is like the amount of material, like the number, and then the contrast, so it's like the size of the things cubed, right? So, and then if you have a surface, so within a surface, like you have 2 points here, separated by distance r. There's always a point in the middle that gives you destructive interference. So it's like if these are rocks that fell here and it's given off, they got to interfere with each other, so you get some kind of thing coming off at a fixed angle. That kills this. That will destructively interfere with that. It'll be down when that's zero. So within the solid, you get zero scattering, right? So you only have this surface region where you could possibly have contrast between, like, so if you're here and here, there's potentially nothing in between to make that interference. So it's kind of a zone here called the parode interface, that's got that size R to it where you could generate scattering. Right, so if your particle is a sphere, like it's gonna be along the surface of that. And your scattering is gonna come in like incoming wave and outgoing wave. So you need points along this that are separated by this distance R, like where the incoming wave and outcoming wave are in phase with each other. So as you change the angle, that distance R changes. Right? In other words, high angle, you get a smaller R, low angle, you get a larger R. So you have that distance R. So anyway, that's the same distance as that distance on the surface. And then if you figure out like how many, like the number of those that can fill up the surface, I think I can do this right. It's going to be like the volume of this R. It's going to be the surface to volume ratio times this times let's see, divided by R squared, R cubed. Yes, let's see. The volume of that thing is going to be the surface area times R, right, and then divided by R cubed. So it's basically going to be the surface to volume ratio for that. So you're going to have like that thing's going to be 1 over R cubed, and then it's going to be the volume squared here. So that's R to the 6. Somehow that should give me R to the 4. This would be giving me R to the 2. Sorry, this 1 by 3 is 2, and then R to the 6. So that gives me R to the 4. In other words, this is binary interference. The volume of one times the volume of the other is R cubed squared gives R to the 4, and R is 1 over Q, so that's 1 over Q to the 4, or Q to the minus 4. So you expect to see this steep in the slope of that. So it's going to be B times Q to the minus 4. B is the surface to volume ratio of the thing. So basically, you expect to see that steep slope. That's going to be the surface of something, a 3D object. If it's a rough surface, it's a little bit less than 4. So it gets 3.3. So it's a really rough surface, but it's a solid surface. So the steep slope means you have a solid object. The weak one means you have this kind of polymer chain. You could solve it. So it goes through the transition. It shows exactly that. It's nice. So that's good. That's exactly the process he wanted to show. He gets the size. He could have gotten the size from doing a fit here to the wrist gyration to a Gaussian, but he didn't do that. That's another thing that's kind of missing, but maybe he did it and he must have done it and realized it didn't match with the computer simulation or something like that. He says a couple other things about when you have the solid object, the steep slope, and then within it, so going to higher Q, smaller size, so within it, he gets the steep, weaker slopes, meaning that the solid objects have squiggly things inside of them. Right, so it's like, you know, whatever you want to imagine that looks like, but so the one thing is an expanded coil. Yeah, there is a problem, like, so he gets this, oh, no, he plots Q, so he normalized Q's 1 over size, and then RG's size, so that gives a unitless number. So he's shifted these all so that the knee part of this thing are all at 1. And there was a race gyrations at 1 here. So here he should have seen that the race gyration shifted, right? As this thing got larger and smaller. He didn't talk about the size. So apparently he's measured the size, but he doesn't report it. The race gyration here, I think. I didn't notice that he reported it, but the RG he reports is from the computer simulation that I saw. So at some point, yeah, he has RG from the simulation, RH from this dynamic light scattering measurement. So he never reports RG for the scattering. I don't think he reports it in this supplemental either. So I didn't notice it was in here. Anyway, so that's kind of an odd thing too. It means because he didn't report it, that means, and he definitely used it because he used it to normalize that thing. That means that it didn't work, like it doesn't fit with his theory. I would take that to be the meaning of that. Like he's got RG here, he didn't report it, so that means it didn't somehow work out. You can kind of pick from here, like you could digitize this and measure it. I didn't do that. So if this thing, so the steep thing should be larger by 20%, right? So this knee part should shift to the left compared to the others. I think no, it should be smaller, it should shift to the right. So it does, maybe it does kind of do that. Anyway, you can fit that. He didn't show that in here. Anyway, so that's where this thing is. It's a pretty good paper to look at. I mean, it's not, you know, it's got a lot of different features of what we're talking about in it. And it's got some kind of topical interest. So Let me see what's in here. Well, Kieran, explain this observation. This is just like explain scheme one, like this picture. Like explain what's going on here. And as best you can, I guess. I mean, I kind of say what's going on here, but basically put it in your own words, whatever. Use dynamic light scatterings, explain how this can be used to obtain the hydrodynamic radius. That's the Stokes-Einstein. This is going to be 2 times diffusion coefficient times time for random walk. And then Stokes-Einstein gives you the hydrodynamic radius from the diffusion coefficient. And then derive the Stokes-Einstein. So that could take you a while, but that's in notes. That's in the notes. So it's in the notes of one here. Whether those are. File 1. There, somewhere. Oops, there. So it's in, that's derived the Stokes-Einstein is kind of the set. This it's basically this thing, right? I guess it's that thing. Basically, it's slide 27. What these had numbers on them. It's just slide 27. Anyway, it's in that region. Just like kind of copy that. This is a Stokes-Einstein equation. So somehow it came, it's one of these from slide 27 to 30. Then, oops, so I gotta go back here. Zhang reports some like, it's kind of like go through what we did, you know, see memory lane type thing. Reports a molecular weight from GPC measurements based on equivalent, blah, blah, blah. Why does molecular weight values actually, they're reflecting the hydrodynamic radius, basically. So if he had more, and that's why they can change size without, when the polymer is still the same. So if he had a viscosity detector, a light scattering detector. So here, oops,
So all that light scattering detector would do is get the actual molecular weight and geometry of the small radius assessment.
yeah, it would give you the actual molecular weight. So it doesn't give you the hydrodynamic size, it gives you the molecular weight, because this I, so I versus Q, like log, it's gonna look like that, like -2 and -1.67, right, or 5/3. So that's the dimension, and then this is that's the RG. And then at this intercept, you just get that for get the number times the size like that. But if you have the linear part here, that would be, you also get a number like that. So this would be like the number of the linear things, the number of the Kuhn units. And then this is the number of coils. And if you take the ratio of the number of coils to the number of Kuhn units, you get the molecular weight. And that ends up being the weight average molecular weight, because this R cubed is a volume times the density gives you the mass. So this is a weight average molecular weight you get out of the thing. Basically, and you can calculate this number if you can't measure that, and divide that intercept by that number you calculated and get the molecular weight. Or you could actually just observe it and take the ratio of those two numbers to get the molecular weight. And that's a physical number. This one, when you do this GPC, so you start with a distribution like that, and you're taking, because it's going down and it's separating that out, each one that comes through is like a perfect amount of dispersed sample. So every second of time, you get a perfect amount of dispersed molecular weight, meaning that the MW equals MN equals MV from the viscosity. So if you do the viscosity one and the light scattering one, and then the other one is potentially giving you this, except it's not a real number, it's versus a standard. And you have like 3 things that agree with each other with the same machine on the same sample. So that's like so nice, you know, because if you have things like that, and these 2 are sensitive to like the size of it, then this one isn't, and you can tell what happened to it. You tell the whole story, more or less the whole story, right? From a simple, it's just like inject it and get that information. So it's like simple, and it's not like NMR, it doesn't take like brain surgery to figure out what's going on, it's just like pretty easy. Anyway, so, but he didn't have that detector, so that's kind of a big problem. He uses coarse grain molecular dynamic simulations, reactive, oh, sorry, we had a couple minutes, I guess, but coarse grain reactive groups are close together. X is the contour length. So I want you to just say something about what does it mean? Like, what is he doing there? Like, without this class, there's no way you can understand what he's talking about there. Demonstrate that you understand what a contour length is and why he's doing that X thing, what difference it makes. So he's not talking about a physical distance X, he's talking about a distance along the chain. And the chains are crumpled or not crumpled. So the physical distance, anyway, there's a physical distance and the contour distance. He's talking about contour. And like, just to explain that.
And that contour is,
The contour tells you that when the two things have a long contour distance apart, that means that the thing's crumpled up. And if the contour distance is close to each other, that means you're only looking at ones with the chain extended. You know what I mean? So he polymerizes it, they stick together, then he measures the distance between them with the computer, with the simulation.
so the longer, I guess, the longer the physical length, the shorter the contour length, if it's a single long chain.
The physical length is always the same. They're always next to each other because they're glued together. So the
Oh,
physical
longer,
length,
longer, that's that.
they're the ones that cross-linked and they're stuck together. They're always the same distance apart, but the contour length is quite a bit different between the two. He shows like this one's, they're right on the same spot on the chain. This one, they're separated by quite a bit.
Yep.
So that proves what he's saying, but you can't really understand that unless you know what a contour length is. So you can kind of look at that and so that's why these things could be important. Like if you wanted to do that and show that it worked, this is what you have to do. And it's nice that he did that. I mean, it shows that the guy's pretty bright, right? So it's good that he did that. It's all coherent and everything. 6 shows a good solvent behaving a power, and then this is just about the power law 1.7 that we did in the Flory-Krigbaum thing. So just derive the Flory-Krigbaum. That's what this is saying. So go through the notes. Everything should be in the notes here at some point. People don't seem to look at the notes, which is a little disheartening. So this is basically the Flory-Krigbaum with the 5/3 at the bottom. So this is the Gaussian. This is the Gaussian with excluded volume, this one. And then because you can't do an integral of that, an analytic integral, then you have to do a derivative. This is the answer to the derivative. You rearrange this to that based on the R0 is the original Gaussian size. You forget about the 3 because this is a small number, and then or big number, large number. Then you end up with the 5, and this thing is up to 3/5. Rearrange that. You just take the first term, that term, rearrange it, get the coil size, which is n is 3/5. So this slide is slide 7 of the second set of slides. Just go through that. That's what it's asking you to do. All right. And how scattering can be used to verify. So scattering is the slope. So the we got 1 second. How scattering can be used to verify that. That's like you could also take that. So if you take like the coil, and then you're going to say it's got a size R and it's got step size L. So you can say like it's going to be n squared, right, for this thing. And then somehow this is going to end up, let's see, I can't do that. I think that fast. N is how many L's are there? So that's going to be your molecular weight N. And then the contrast for this thing is a function of size. Oh, it's a function of size. That's it. It's a function of size. So N goes with the size squared, right? But no, so you get more N for bigger size. And then within the same, or maybe that's it. Like N goes with the size squared, so you get the dimension out of it. Basically, you can use this thing to get the dimension thing, but I didn't do it exactly right. So basically, the scattering gives you that dimension. I can show you maybe on Monday or something how that works. I don't think I can do it right now. I could do it, but it would take more than 1 minute, I think. Anyway, so anyway, I'll help you with that. Or you can just say like it's 5/3, that's kind of how it works. So hopefully that's okay. So anyway, it's the paper.
question, but I think
Yeah.
that only applies to me. I saw that you were teaching a class in the fall, like about plastic.
Yeah,
Is that gonna be kind of similar to this one?
no, it might have like invited speakers and stuff.
Okay,
So it might be a little bit like Africa, Solar Power Africa thing.
Yeah.
A little bit like that. Depends how many people.
I need another committee elected
Mhm.
and I don't wanna take a gamble.
I mean, it's not gonna be It's not gonna be like a high level,
Yeah,
you know, it's gonna be, there's a book.
okay,
I can show you the book next class. I can link it up or
okay,
something.
I think that I think that Juan and I are the only undergrads. Well,
Okay.
only juniors
Uh-huh,
who aren't like graduating.
Yeah.
so.
all right.
Uh.
Yeah, so, yeah, it should be, it won't be this level, you know? It's not gonna be like this, but so it's a dual level